Chapter 12, Number 52. On Apollo moon missions, the lunar module would blast off from the Earth's surface and dock with the command module in lunar orbit. After docking, the lunar module would be jettisoned and allowed to crash back onto the lunar surface. Seismometers placed on the moon's surface by the astronauts would then pick up the resulting seismic waves. Find the impact speed of the lunar module given that it is jettisoned from an orbit 110 kilometers above the lunar surface and moving at a speed of 1,630 meters per second. So that's our situation. We start at some height, and then it spirals down and hits at some velocity. We're going to do an energy balance, and we're going to say that the energy at the start, when it's first jettisoned, equals the energy when it hits the surface. When it's first jettisoned, it has a kinetic energy part, which is 1/2 the mass of the lunar module, times the velocity it's moving squared. And it has a potential part, which is minus g mass of the moon times mass of the lander over the distance to the center, which is clearly the radius of the moon plus however high it started. And then at the end, it has an energy which is equal to its kinetic energy, 1/2 the mass of the lander times v2 squared. But also, it still has kinetic energy because it is still has potential energy because it is still above the center. It's not at infinity, which is where that energy is 0. So we have g times mass of the moon, mass of the lander. Now it's only one moon radius away from the center, and so we just get that. So in one sense, this is a quote-unquote just plug in numbers and solve for v2. Not particularly fun, but entirely possible. For instance, we can see that we can cancel all of the masses of the lunar module, because they're in all terms. And so I can rearrange, and I would get something like, we might cross-multiply by 2 and isolate v2, and we'd have v2 is, we'd pick up a factor of 2, so we'd have v1 squared, and then, plus, and we have, because of these factors of 2, here and here, I've cross-multiplied, so I pick up a factor of 2 here, and I have gm over r, and then I have 2gm over r plus h, and all of it needs to be square rooted. Here we'll need to go to our source, such as maybe Google or the back of the book, and remember that we get the radius of the moon is 1.74 million meters, and the mass of the moon is 7.35 times 10 to the 22 kilograms, and if we plug all of those things in, we end up getting 730 meters per second.